Hello, everybody. Welcome back. Today we're going to be looking at Unit 3.3, which is all about solids, liquids, and gases and their properties. So let's get started. So I'm using a simulation here from a website called PHET, P-H-E-T, and it's great. We've used it before. And this first demonstration is just to show you some characteristics of solids, liquids, and gases. You can see here that solids are very tightly packed together. Remember, we talked about that crystalline lattice structure. They do have motion, the particles do have motion, but there's not a lot of movement. Okay. If we look at a liquid, however, okay, liquids have more motion, okay? Intermolecular forces are at play here, okay? You will notice that on occasion, we'll see a couple of particles jump off the surface there and escape into the gas phase, and that can happen. Think about a pot of water sitting out on the, out on the kitchen counter. Evaporation does take place. Things can go from liquid to gas below the boiling point. It's just if that particular particle had enough energy to escape into the gas phase, that would happen. So we're seeing a lot more movement with a liquid. In the gas phase, of course, we're going to see faster speeds, greater distance between the particles. At this point, intermolecular forces are really not a factor at this point because the particles are so far apart from each other. Now, let's talk about phase changes. All right, here we are seeing a sample of ice. Okay, those little tiny particles, if you can focus your eyes in on them, you can see that bent shape, almost that Mickey Mouse shape of water. And it's in the solid phase right at this moment. And if you'll notice, there are these gaps, okay? Most solids don't have that. Water is a little bit unusual in that its solid phase is less dense than its liquid. That's unusual. Water's not the only substance that is the case, but it is unusual, and that's why ice floats, whereas most substances, their solid form would sink in their liquid form. But let's think about phase changes, okay? And we'll use water as an example. So I'm going to add a little bit, just a little bit of heat here, okay? And if you'll notice, over time, those gaps that were in the ice are starting to sort of contract. Okay, so now we're in the liquid phase. It's more dense. Again, that's a little bit unusual. Okay, but we're in the liquid phase now. Okay, the motion you can see, they're still moving, they're still interacting, but they're moving with a little bit more energy. And I'm going to add a little bit more heat. Okay. They're starting to move with even more energy, even more. Add a little bit more heat. And now they get enough energy to escape into the gas phase. So what I want us to think about is when you take a block of ice or anything in the solid form and you add heat to it, and it melts, and then you keep adding heat to it, and it boils. What are you breaking? What are you breaking to go through the melting process, to go through the boiling process? You are breaking intermolecular forces. You'll notice, guys, even in the gas phase, the water molecules themselves are still intact. I did not rip that molecule apart. I haven't broken covalent bonds. I've broken intermolecular forces. Okay, And the same can be said if we cool it down. Let's take that gas and cool it down. And you'll notice that they're starting to clump together a little bit more. They're not moving quite as much as they were with as much vigor as they were. And now we're in the liquid phase. And ooh, now we're into the solid phase. So what is being formed when you cool a sample of water vapor into the liquid phase and then cool it even more into the solid phase? Intermolecular forces are being created, formed, okay? It's not breaking those covalent bonds, okay? So I just wanted to go through that with you. Now, what might an AP question look like in terms of states of matter and going through phase changes? It might look something like this. So this question says, the box below represents a closed container with liquid ammonia, okay? And you can see the little ammonia particles. Ammonia is NH3. In the box on the right, represent the same sample of ammonia after undergoing complete evaporation. So what would it look like from liquid to gas if you were going to draw in the box? So if you want to pause the video here, you can, and think about what that drawing would look like. All right, let's see how you did, okay? Your drawing should look something like that, okay? Now there's a couple of things I want you to notice here. To get full credit for a question like this, you would need to have the same number of particles as in the drawing on the left. There were 6 ammonias on the left, there should still be 6 on the right. It's in a closed container. Since it's in the gas phase, you should draw them with space between the particles so that it's clear that it's in the gaseous phase. And the third requirement is that you kept the molecule together, okay? Meaning each molecule is still intact. You did not break the covalent bonds, okay? If you had drawn something like, you know, let's say that's the center atom, but then you had drawn those hydrogens separately, that would be marked wrong, because that would tell the graders, oh, you think evaporation or boiling involves breaking covalent bonds, and it doesn't. Okay, so that's how you would get full credit on a question like that. So I just wanted to show you what a question involving states of matter might look like. So that was a short little lesson. I hope that you've learned a little something, and I look forward to seeing you next time.